In this video, we're going to briefly consider sums of infinite series and everyone's favorite, error bounds on those, estimating those sums. Now, there's only one situation where we can find an exact sum with a formula. So we can find the exact sum for a converging geometric series. And exact for an infinite, exact sum for an infinite converging geometric series. That formula you should know is a sub 1 over 1 minus r. So we see these problems all the time. It might be something like, let's say 4/3 minus 4/9 plus 4/27 minus 4/81 plus dot dot dot. And to figure this out, our first term is 4/3. We can see that what we're multiplying by every time is negative 1/3. And so in this case, we have 4/3 over 4/3. And once again, our sum is 1. It is not always 1. That's just the way this one happened to turn out. All right, so let's move on to the error bounds, which is the tougher thing. So alternating series have a special error bound. Do not make the mistake of using the Lagrange error bound when you actually have an alternating series. Now, there have to be a few things true about this alternating series. First, it has to be convergent. Now, how do we know an alternating series is convergent? The terms go to 0. Terms go to 0. And the terms get progressively smaller. And just so we understand why it is the case, let's see if we remember this. We drew a diagram of this where we start at 0, and let's say the real sum is right here. So there's our real sum, and I put in my very first term. So this is a sub 1. It has an arrow to the right because it's a positive term. And after one term, here's my sum. And now I'm going to take my next term, and what happens is my next term overshoots in the other direction. So this term is a sub 2. Now, and we end up right here with the sum of two terms. Now, what I want you to notice right here is that the distance, I want to get my highlighter here, the distance from the real sum to sum 1, that's my error. Let's label that. That's the error. And I want you to notice that that distance is less than the next term, which is a sub 2. And that happens for every term, so I could keep drawing them back and forth. But each time we can see that the error, whoops, don't want that one. Let's try a pen here. The error is less than the absolute value of the next term. One thing to note, that if you use this on a free response, you do want to make sure that you comment that you have a convergent alternating series. That's the only time you can use this test. All right, so this brings us to the Lagrange error bound, everyone's favorite. In the Lagrange error bound, the formula says that the error using n terms is less than m over n plus 1 factorial times x minus a to the n plus 1. So let's just make sure we label what is going on here. So first off, this e is the error using n terms. All right, then m right here is the max derivative, the max of the n plus 1 derivative, max of the n plus 1 derivative on the interval from the center, which is a, to a plus x, however far x is from a. Actually, that's from a to x, rather, on the interval from a to x. All right, x right here is the farthest you are from the center, farthest from the center. And a right here is the center. All right, so I I think we've taken care of what we need for that. So let's move on to actually doing one in a problem. So here's a problem, and I would encourage you to pause the video right now and try this on your own. And when you're done, then you can continue playing and seeing the solution. All right, welcome back. So let's take the solution of this particular one. We are finding the error using 3 terms. That was a very funny E. There we go. Error using 3 terms equals, I'm going to come back to m. Down here, I know I'm going to have 4 factorial. And I know I'm going to use a Taylor polynomial centered at 0. That makes sense because 0.2 is so close to 0. So 0.2 is the farthest I am from the center, minus 0, which is the center of my Taylor polynomial, and that's going to be raised to the 4th. Now I need to know the maximum of that 4th derivative. If we've worked with these a lot, we recall that if y is sine, then y prime is cosine, y double prime is negative sine of x, y triple prime is negative cosine x, and oh look, there it is. The 4th derivative brings us right back to the sine of x. All right, and I think about my sine function, or in this case my 4th derivative, and I recall it starts here and goes up, and I can see, oh yeah, my derivative at 0, my derivative at 0.2, this is increasing, so I'm going to have a much higher derivative at 0.2. So the sine of 0.2 becomes my m, and now it's just a matter of putting it in my calculator and getting an answer. Just remember that oftentimes on the AP, they're not going to make you go through finding all those derivatives. They're actually going to just tell you what that value of m is.